All right, everyone. Welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Nicholas Carlini. Nicholas is a research scientist at Google Brain. Before we get going, be sure to take a moment to hit that subscribe button wherever you're listening to today's show. Nicholas, welcome to the podcast.
Great to be able to talk to you.
Hey, I'm really looking forward to our conversation. We're going to dig into some of the work you're doing around privacy and security for large machine learning models. Before we get to that topic, I'd love to have you start by introducing yourself to our audience. How'd you come to work in the field?
It's kind of funny. So I started out as just a core computer security researcher. I did research in just system security for several years, and the first several papers of my PhD were all just system security, like exploitation of hardware things. And then I needed to write my PhD, and I didn't know what I was going to do a dissertation on. And so I tried to find something where it looked like there were a lot of open problems where no one knew what they were doing. And this was in 2016. And it looked like there was no one working in machine learning doing security there. And so I decided that might be a fun thing to do. And so essentially, my first couple papers in machine learning, I just replicated what I had done before that and just found defenses in machine learning that people had written that looked like I could attack and just attacked those.
What are some examples?
The first like real paper that I had sort of in deeply in the machine learning space was this paper towards evaluating the robustness of neural networks, where there was a paper the year before by Nicolas Carlini that who I now is affiliated with the team that I'm working on. But he wrote a defense called distillation as a defense to adversarial examples. And it was like one of the first serious attempts at defending against this problem of adversarial examples, which is this phenomenon that you can take any machine learning classifier and you can really easily fool it by changing the input imperceptibly. So you can take an image. The canonical images, you have this image of a panda, and I can introduce a very 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 small perturbation to turn it into any other thing that I want. I can make a machine learning model classify it as the image that they did in the paper was a gibbon, but I can do guacamole or anything that I want. And so the first paper that I attacked was this defense to try and make this not possible. And we just showed that we could break the defense, and it was no more robust than just a baseline classifier. Yeah, after that, I spent a couple years trying to sort of understand this specific problem of adversarial examples. And then from there, I branched out more broadly to the question of other interesting security problems, and then also other interesting privacy problems, where we try and study not just how hard it is to attack a particular classifier, but also what about the user data that was used to train the classifier that or the in general the language model or the diffusion model, as we might talk about later today.
The adversarials problem was one that was, very hot. I guess around the time that you were working on it, and I hear a lot less of it recently. Is it? I don't suppose it's been considered a solved problem. Is it just that it's kind of a theoretical problem that it isn't quite as practical as folks were maybe initially thinking?
I think the reason why people have been spending less time, is that people still publish quite a lot on it. I think the reason why there's maybe a little bit less attention, though, is because of how hard it is.
We're just going to sweep this under the rug.
Yeah, that kind of thing. Where, like, for a couple of years, there was really a lot of optimism that we'll be able to figure this out. Like, this is a flaw in machine learning. We'll just need one or two new ideas and it will be done, and we'll just sort of move on to the next hard problem. Like the paper that introduced it, like didn't really consider this to be like a big giant. This is like no one knows what they're going to do. It was like called like intriguing properties of neural networks. Like here's this sort of cute thing that we found. Like isn't this interesting? Um, and then it turned out that people have written like several hundred defenses trying to defend against this, and like only a handful actually work. And just is really hard to design defenses that work. And then yeah, and then also at the same time, like the threats aren't just there. So like a lot of people got into adversarial machine learning by looking specifically at this adversarial example problem, but then once they realized like there are more attacks and some of them aren't quite as challenging to defend against as this one particular problem, and there are other things that are worth studying, people sort of branched out from there. I mean, I did the same thing. And I think it's good that not everyone is only working just on that one problem. I still would like to see a solution to adversarial examples, but it's been hard.
Now, refresh us on the problem and kind of solution directions there. I kind of remember it very roughly as you inject some kind of targeted noise and you can manipulate the classifier, and the defenses seem to be, you know, broadly describable as like different ways of regularizing the input so that the noise is less has less of an impact.
Yeah, this is exactly right. So the problem is I have a classifier, and you can attack it by feeding it an input which is imperceptibly different from any normal input. And you can do this on images, you can do it on audio, you can do it on natural language processing, you can do it on video, like all the domains. You can have two inputs that look the same to a human, but to a machine learning model, they'll give you completely different outputs. So how do you attack this? Maybe this is the first question. And this is actually it's fairly straightforward. And this is like really what the first paper that I did tried to do is to lay out like what is the right way of attacking one of these classifiers. And so like, the way you train a machine learning model is with gradient descent. You just take gradients with respect to the weights, um, and you feed in many inputs and outputs. The way you attack a machine learning model is with gradient descent. Only instead of taking the gradients with respect to the weights of the classifier, you take the gradients with respect to the input. So you say, for every input in the image, let's imagine we have pixels on an image. For every pixel on this image, which way should I change this particular pixel to make the model do less well? And any given pixel change is not going to do very much, but a high resolution image is going to have millions of pixels. And so like the contributions add up, and after not very much change, you can very easily figure out a new input that is very, very similar, but still is now classified very differently.
Yeah.
So that's the attack side. Now let's talk about the defenses. For a long time, people tried very ad hoc defenses. Um, Various kinds of like maybe weight regularization solves it. Maybe training with a different loss function solves it. Maybe training on soft labels solves it. Maybe a distillation solves it. Just like all these things that just people believed might help, and it turned out that basically none of them worked. Like you could like and when I say none of them worked, what I mean is like it did not make the model any more robust than the baseline.
I could swear I saw a paper saying that all those things worked.
Yes, no, exactly right. And then there was a paper by Alexander Madju's group at MIT that was really the first defense that actually did anything meaningful, which introduced adversarial training. And it wasn't the first time this had been proposed, but they sort of did it right. And adversarial training basically says all I'm going to do is I'm going to take the adversarial examples that I can generate with an attack and train on those. So you do the most naive thing possible. I will just like train model, generate adversarial examples, use those adversarial examples to train model, and you repeat this like for a very long time. It's very slow because you have to do this a lot. Future papers sped it up, but the baseline is very slow. And at the very end, it works in that the classifier is somewhat more robust, but it doesn't solve the problem. So you have let's take a task like CIFAR 10 classification. Standard classifiers can now reach 99% accuracy. So it's a 10 class classification problem. They can get it right 99% of the time, absent adversarial examples. If you attack these classifiers, it goes down to 0%. The attacker can bring the accuracy down to 0%, which is very, very strong. With adversarial training, it recovers maybe 60% accuracy. This is good. 60 is better than 10%, which is the baseline of
Right.
a 10 class classification problem. But like 60% is like just over a coin toss. Like, in normal areas of security, when we say defense works, we mean like if the attacker tries like a million times, they'll still fail. Here you try twice and probably one of them works. So like, this is positive progress, but it is nowhere near where we want to be for like an ultimate defense. And since then, there have been a lot of other refinements of adversarial training. There are a couple of other schemes that actually work, but for the most part, like the dominant empirical scheme is adversarial training.
With regards to the practicality of the attack, the threat, like, is it something that we've seen examples of in the wild?
Yeah, not so much. And this is one of the things that I've been thinking about is why. It seems to be the case that okay, so often, if you're a real person attacking a system, you're going to take whatever's the easiest approach. Like, I'm not going to go like, oh, look, a machine learning model. Let me attack the machine learning model. If there's like something else that's easier to attack, I'm just going to attack the easier thing first. And for most things, the easiest thing to attack is not the machine learning model. There's some other component that's easier to attack, and so you're going to attack the easiest thing available. There are a couple of cases where the machine learning model is the easiest thing to attack, or is the primary thing that you can attack. So you can think, let's imagine I have some website I'm running that I want to make sure is like people can upload images to, but you can't upload any kind of abusive content. So most websites fall into this nature that upload user content, and they're going to have some machine learning model in the background that's running where they want to make sure that you can't upload content, and they'll check it with their model. If the model flags it, maybe it goes to human review, and maybe there's also some other human review. But for the most part, it's like the model checking most things. And in these systems, like you do see these kinds of attacks. They don't have to be as sophisticated as these like adversarial example things that people do now, because the systems are, again, easiest path possible. It turns out that for most of these things, you add a black border to your image and the classifier just fails randomly anyway. You may have seen people sort of do this where they put like they like superimpose like a fake window on top of an image, and like there's an object behind the window, and we all see like the object behind the window, and but the classifier just says it's a window, and it's like, well, yes, it's a window, but like there's something behind the window.
I guess I do see that a lot, like on YouTube, where folks will have like they'll just apply weird effects to like sports simulcasts or whatever that they want to evade the classification system for a while.
Exactly. And so people will do like whatever's the easiest thing, and as long as the easy thing is something like this, then they're going to do this. And the
And
problem with
that's a
adversarial
lot easier
examples.
than adversarial examples. Yeah,
Exactly. Yeah,
got
and
it.
so people will do this, but like the ultimate problem of adversarial examples, like the reason I think it's important is like it shows what the fundamental limit of the vulnerability is going to be. It says that like even if you solved like all the easy cases, which we definitely should do, like it's important to solve the easy cases. Like there's eventually you'll run into this problem of adversarial examples, and people will be able to still evade it there. But we should make it not so trivial. But yeah, this is the general problem right now.
And so you mentioned that you ran off and found some easier problems to solve. One of those being kind of privacy.
Yeah, so a lot of people working on adversarial examples, and my first actual internship at Google Brain, we wanted to look at privacy of machine learning models. And so what privacy here means is your so you train a machine learning model on a bunch of data. Sometimes this data doesn't matter what you train on. Like, if we're training on MNIST, this is a data set of like handwritten digits that people were paid to like write numbers on a piece of paper, and then they scanned them. It was collected in the 90s. Like the privacy of the way that this person in the 90s wrote their sevens is not so important. But there are lots of machine learning models today where they're trained on sensitive data. This is people's text messages, emails, medical images, these kinds of things. And you want to make sure that when you train a model on some sensitive data, the model doesn't go and leak the data for anyone who can access the model. So the general way that this would work is what you would like to be able to do. Like, let's suppose we're living in a very nice world. Some hospital that has lots of patient data could train like a cancer detector or something on um, all of their patient data, and then they could release this model to the world, and then anyone could go and download this model from any other hospital in the world that didn't have as much data, and they could sort of scan their images or something. Now, I mean, obviously, you want to make sure that the model is good, and like like there are all kinds of like ethics and things I'm just completely put aside. But like this would be a thing that people would like to be able to do. But it turns out that given access to the model, oftentimes the model leaks information about the individual people who are used to train the data set. And this means that you can't just go and release many of these models in this kind of way, because, I mean, you just can't violate the privacy of the patients who were used to train the model. And so uh, several papers that we wrote looked at this privacy problem, first for language models, um, and then extending it into other kinds of vision models.
And the vision models are diffusion models of the kind that are used by Stable Diffusion.
in privacy attacks, there are two different kinds of privacy attack, or there are at least three. But let me. So the simplest privacy violation is one that you might not even consider a violation, which just asks, can I detect if your data was if you were used to train the model, yes or no? So this is like it's called membership inference. It tries to infer whether or not you were in the model's training data set. Um, the reason, I mean, okay, so there are some cases where this matters. The first question is, why should I care about this problem? The reason why this matters for some questions is, let's suppose I have a data set and I know that everyone in the data set either has disease A or disease B, like we're classifying between two diseases. Your presence in the data set tells me that you have one of these two diseases. I don't know which one, but now I've learned something sensitive about you. I've learned that you have one of these two. Um, and so this is a problem, but it's sort of limited. And we've studied privacy of just standard classifiers under this setting, of this membership inference setting. But you can't do. It's sort of hard to convince some people that this is a real threat, and for a good reason. Like there are lots of settings where like it just doesn't matter if I'm in the data set or not. But this attack is sort of the fundamental building block that allows you to do what's called training data extraction or reconstruction, which is the much stronger attack of, given the trained model, can I actually pull out the image of the person that was in the data set? And this is the thing that like you don't really need to motivate the privacy of, because it's obvious that we would like to be able to train models and not be able to pull out individual people from the data set. And this is what we did for these diffusion models, including Stable Diffusion and Imagine and a couple of other smaller ones, where we were able to show that given the model, we can just like find a way to recover these individual pictures of people or other things that you may not want to be recovered.
Mhm. And the fundamental mechanism that you're exploiting is that these models are so large, they have, to some degree or another, a tendency to memorize aspects of their training data. Can you talk more about that?
So it's interesting. Okay, so they're very vague. So Stable Diffusion is 900 megabytes. Sorry, 900 million parameters. So the lowest, like the smallest you could make it probably is something like 900 megabytes. In practice, it's a couple gigabytes because you want a couple bytes per weight. But like, it's like 900 million parameters. Um, you can imagine a world in which it's maybe 900 megabytes. But it's definitely not bigger than like say 4 gigabytes. The data set that it was trained on, though, is enormous. It's like 10 terabytes. It's 10,000 times or 1,000 times bigger than the model. And so, like information theoretically, it's just not going to be possible for the model to memorize all of the data, right? I mean, like you just like count bits. Either the diffusion model is like the world's best compression algorithm that's like 1,000 times better than anything we've ever developed, in which case we're not going to use them for classifying images. We're going to be using them as a compressor, which is not the case. Or it can only memorize a small fraction of them. And so in practice, what happens is it turns out these models memorize not even a significant fraction of the data set. Like we found, we spent some pretty good amount of effort, and we found, I don't know, the memorization rate is like 0.00001% or something. It was sort of like we found like 109 memorized examples in all of Stable Diffusion. Now I'm sure this is a lower bound. I'm sure that people will be able to make this larger, but I don't expect it will be like any significant fraction of the data set.
And are you distinguishing between like some full memorization versus partial memorization that can be?
Yes. Okay. So our definition of memorization is incredibly restrictive. What we are looking for is almost verbatim pixel for pixel matching of the image that we can pull out from the original image. So like we're basically saying like our definition is roughly as precise as saying the difference between the uncompressed and like the JPEG compressed version of the image. Like we and the reason why we make this very precise restrictive definition is because this was one of the first papers that studies this problem. And the first thing that you should always do with problems is show like this is possible. And once you know it's possible, then you should show like let's like fully understand what the problem is. And there are a lot of people who just didn't believe that it would be possible to do any kind of extraction attacks on diffusion models. And so we wanted to start off by just like establishing something that everyone can agree with, that like everyone in the world should agree that this is an extraction attack. Like the images are so close to basically be indistinguishable, like we have succeeded at this. And now we can start talking about, what if I can extract only the foreground image but not the background? Like, is this generalization or is this memorization? What if I can extract an image that is an image of of the person, but like in different lighting or different sort of other environments? Like, what if it gets, you know, contrast adjusted? Like, there are all sorts of other things that probably are still closer to the memorization side, but like, there's maybe a legitimate argument that someone could make that this is generalization. And so what we want to start by doing is saying, like, let's do something that irrefutably is memorization, and then from there we can move on to the like other more nuanced definitions.
And so does that low memorization rate kind of neutralize the extent of the threat, or is memorization just kind of the starting point, and the threat is comes from broader effects?
Okay, so to be clear, like, a low memorization rate is good in the abstract, but like, let's suppose it was okay. So Stable Diffusion, this model we attacked, was trained on images scraped from the public internet. So like, we don't get like anything terribly sensitive. We get mostly memorization of like public celebrities. Let's suppose that this model was trained on medical data sets, like other people have proposed in the past. Like, people have proposed that we should train diffusion models on medical data sets, generate images from them, and use this as a privacy preserving technique. Um, if your medical images were one of the 109 medical images extracted, you wouldn't go, "Oh, it's fine. Like, it's okay that you memorized my images. Like, most of the other people were safe." Like, you would be rightly, pretty annoyed. Um, and like, this is sort of the problem with privacy, is that you can protect the privacy of almost everyone and still be in a bad place because you didn't protect the privacy of the few people that actually mattered. But yeah, but on the whole, like, the total impact is that from our attack, yeah, like you say, is quite low.
Is there any characterization or pattern of those images that were memorized that jumped out? Are they um, you know biased one way or another in the data set? Yeah,
So the primary cause that we can identify is duplication.
got it.
For stable diffusion, the only images we can extract are ones that are repeated many times. But there are lots of images that are repeated many times, and only some of them get memorized. And we don't have a good understanding of which ones are the ones that are like there are some images that are repeated like 10,000 times and aren't memorized, and other images that are repeated like 100 times that are. And so it's very weird that like there is some property. We just don't know, like, maybe it's just luck. Maybe the model just gets lucky and it happens to memorize some images over others. We don't think that's the case. We have um, okay, here's one fun experiment that shows that's probably not just luck. Um, we can train smaller models on data sets ourselves. We can train smaller diffusion models and smaller GANs. GANs are another kind of generative image model on some data sets that we control, and we can then study this sort of much more rigorously. And when we do this, we can compare, are the images memorized by diffusion models the same as the images memorized by GANs? And it turns out that roughly half of the images that the GAN memorizes, the diffusion model also memorizes. And the diffusion model only memorizes like a very small fraction of the data set. So like, you're not just like, it's not just luck. Like, there is something to do with these images that make them more likely to be memorized. We just don't really know what it is that like makes these ones be the like, and now I will memorize you, as opposed to the other ones.
Yeah, some period of time in exploring these privacy issues, there was always this question about black box versus accessible models. In the context of stable diffusion, that changes it a bit because it is an accessible model. Can you talk about that dynamic?
Yeah, sure. Yeah, so this is the threat model that you're going to operate under for how you want to do this extraction. And yeah, people like, there's varying degrees of access that the adversary might have to the model. So in the case of stable diffusion, we have complete access to the weights. We can do like literally anything that we want. For our paper, though, we studied this like complete black box threat model, where the only thing that we assume the adversary can do is query the model. So I can just like ask the model, please generate an image for me of X. and it'll give me an image. And like I assume that this is the only, even though we have more access, we assume this is the only access we have. And the reason we make this limiting assumption is just because, first of all, it's most practical, but also because it's easiest. Like it's harder to develop attacks that use more knowledge. If we sort of come up with the simplest attack first, we'll start there. And so um, okay, so this is why. But then it turns out that for the problem of, for example, membership inference, where I'm trying to predict if you're in the data set or not, there's basically no attack that works better in the white box setting than in the black box setting. So the white box setting is where I assume I have everything. Black box setting, I assume I just get to see the output. It turns out for membership inference, like we do not know of a method that uses the sort of internals of the model in any way more than that does better than just looking at the output of the model.
Got it. So that's a practical result based on what we've seen so far, as opposed to some theoretical.
Yeah, exactly. Like, and so it's possible there's something that you could do much better. There's like maybe one or two papers that are starting to show that you can do something if you know the weight, but they make this is some from some of our collaborators at DeepMind. They make some ridiculously strong assumptions about like I know every other image in the data set except yours, and I know the initial model random seed, and I know the order in the mini batches. But if you know all of these things, then white box access like can help you in a meaningful way.
You probably have the training data and you don't need to extract it.
But like it
Right.
assumes that like every other one except you. So technically, it's sort of a well-defined problem. Um, but yeah, for the most part, like it's interesting that white box and black box are so sort of. It seems like you have so much more power, but it's been hard to take advantage of it.
And so it sounds like the interface for extracting the training data is through prompting.
Yeah, definitely. So all we do, it's the most naive attack. So what we do, we take a prompt that might be in a data set, and we ask the model for like 500 images of that prompt. Suppose the model didn't memorize. If you give it the same prompt, you should probably see different outputs. Like the model's a randomized algorithm, and so it's going to give you different outputs each time you ask for the same image. And so it might be similar, but like, if you ask for a picture of, some flowers, it's going to give you a picture of some flowers, but there are so many arrangements that you could do this under. It's going to give you different ones each time. But let's suppose I find some prompt and I ask it for a couple of images here, and it gives you the exact same image like 50 times. Okay, one of two things is true. Either the model has just decided this is the only image that could ever exist for this caption by itself, or there is some reason that pushed the model into having this belief. And probably what that was that there was some training example in the data set that had this prompt, this caption, and that the model was sort of taught that the answer should always be spit out this image. And so like literally the only thing that our attack does is it just samples from the model a couple hundred times, and then we just search to see among the generations with the same prompt, do we get the same image out like 5 or 10 times? And if the answer is yes, we predict this probably is a memorized image. And doing this has exceptionally high precision. Like almost never do we identify things that we think are memorized when they're not, because it's so unlikely that if you asked for any normal prompt, I mean, imagine you sort of asked two people to draw the same image, and you sort of gave them some unspecified task, they would probably give you wildly different images. But if you asked them both to draw the Mona Lisa or something, they'll give you at least, I mean, if they're reasonable artists, they'll give you at least something that looks very, very similar to each other.
And are the prompts, generally speaking, of the nature of the Mona Lisa, or are they more like long tail prompts?
We look for duplicate prompts. So sort of from that definition, they're not long tail. But I see. So we sort of try and find prompts like from the kind of data that was used to train Stable Diffusion. Um, but the kind of data that was used to train Stable Diffusion it's like a distribution of a subset of the internet, but it's not like a sort of a natural subsampling. It's like whatever happened to be their subsampling algorithm. And so there are some like somewhat obscure things that are included in the data set that is repeated many, many times. And this is sort of just like an artifact of dataset collection. Like it's very hard to collect data sets. And sometimes you end up sampling some part of the internet a little bit more often than some other part. And it turns out that in that one part of the internet, like the same image is repeated many, many times. And so we get you know, like we can extract images of some people that are fairly famous people, like published a dozen or so books and have a Wikipedia article associated with them and give talks all over the world, but like aren't you know household names. And but like, and then there are other people that are sort of we can't do this for, and again, we don't know what the reason is for that.
Do you speculate that it's because you aren't able to identify the correct prompts, or that they're probably not memorized? Do you have any indication one way or the other?
Yeah, so even when we feed the like actual prompts that we use to train Stable Diffusion, we don't get the memorized versions of those people. So it's still entirely possible that the model does memorize them, but we can't get it. I think it's unlikely, but it wouldn't surprise me if someone next year told me, "Here's a paper that shows how to do much better." Okay, when I say it's unlikely, I think it's unlikely they're memorized like in this bit for bit sort of definition kind of thing we're working with. I think I would be, I don't know, 50-50 odds that like we can get quite a lot more extraction by looking at sort of approximate definitions. Um, so we've started to do this in the case of language models, where we've started to look at approximate definitions of memorization for language, and it looks like there's like factor of two, factor of five difference between verbatim and approximate memorization. If things sort of continue to this in the vision domain as well, we might see something similar. But yeah, I don't have a. I mean, this is sort of very early. Like the paper, we finished the paper like 2 weeks ago or something. So I think yeah, we're hoping to answer a bunch of these questions.
How many prompts are you testing?
Yeah. Okay. So we test 350,000 prompts, and of those, 109 are memorized. And so this is for Stable Diffusion. Okay, so there's two different ways we try and do this. Yeah, so this 350,000 and in 109 images is like this naive just sample from the model thing. Um, for we also study Imagine, which is this similar kind of model trained at Google, and for that model, the rate is much different. So for that one, the model is much slower to query, so we only query 1,000 prompts. But of those 1,000 prompts, we get 23 memorized images, I think. And so the rate there is orders of magnitude higher. But the experimental setup is different, so like we can't really directly compare these numbers directly, but like it looks like there are differences between exactly which models we use to get these numbers. And the other thing is, for these bigger models like Imagine, it's possible to explicitly go looking for out of distribution images that are more likely to be memorized than just like standard things. So we have a fairly complicated proposal for how you find out of distribution images, but under some definition of distribution, um, the models are much more likely to memorize out of distribution images that are repeated infrequently than in distribution images that are repeated infrequently. And we have a couple numbers on that in the paper. I think we test 500 out of distribution images on Imagine, and we get like 9 or something. But the out of distribution thing didn't work at all on Stable Diffusion. So like there are a lot of these questions that we we don't really understand what's going on for.
And on the stable diffusion side, the training data set is well known. Are you accessing? Is it well known on the Imagine side, or do you have unique access because you're Google Brain?
Yeah, it's not this model is not made generally public, but yeah, we have access to the Milad Nasser is sort of the person on our team who sort of worked with these people to be able to sort of access the data that they have.
And so, with 350,000 prompts on the stable diffusion side, you're not handcrafting these prompts. Is what is the pipeline from the data set to the prompt creation?
It's like the simplest thing you can imagine. We take the data set, we sort of sort by duplicates essentially, find the prompts for those things, and then go in that order.
Okay.
So it's like just like let's again let's show it's a problem first, and then we can go and start studying all these other things. Like we're sort of give the adversary all of the power that they like could possibly have, and then from there we'll try and refine to make sure to see like what if we can do if we don't have the precise prompts. Usually they're quite short anyway, so But yeah, we sort of start with giving them the most power, and then sort of we'll work our way back.
And do you have you tried like um I don't know if this would even be interesting, but like my thought is going to like fuzzing of the prompts. Once you get a prompt that works, like fuzzing it to see what happens.
Yeah, we not vigorously.
Okay.
Yeah, we tried this a little bit, but
Nothing interesting jumped out at you.
yeah, nothing interesting yet.
And how dependent is how stable are the results? How dependent are they on like some random seed, somewhere, that kind of thing?
We don't know.
Okay.
It's like so we had some small scale experiments. We looked at this on CIFAR 10, but we don't have any.
That was one where you trained your own model.
Yeah, we trained our own models on. So training diffusion models is actually very slow, very expensive. And so the best that we can do for running a bunch of these privacy experiments is to try training models ourselves. But
Awesome, awesome. So that's kind of the privacy side of your work. At the risk of rushing through it, you also do some interesting stuff on exploring data poisoning. Let's maybe jump into that briefly.
yeah, so yeah, two sort of broad things I'm interested. Yeah, privacy and security. And the security side, one of the things that we've been looking at a lot is this problem called poisoning, where the question is, what happens if the adversary controls a small fraction of your training data set? So let's imagine that I'm, for example, training stable diffusion on a data set of images scraped from the public internet. Um, Not everyone on the internet is nice. Some people just want to watch the world burn and will like upload content that is bad. And so the question of training data poisoning is what happens if someone can control a small fraction of the data that you're training machine learning model on. And starting, yeah, maybe 2 years ago, we started looking at this problem um, because of how the way people use or train machine learning models has started to change. So 5 years ago, if you were going to train the best machine learning model that you could, what you would do is you would like just go take ImageNet or something, one of these well understood data sets, and train a model on that. And the probability that you can poison the data set is essentially zero because like ImageNet has been around for a long time. It's a well understood data set. You can't modify it. Like it exists as an artifact. But recently, people have started to train models on uncurated and unlabeled data because it's just been shown to be a lot better. And this started with semi-supervised learning and then went into self-supervised learning where it's like just better and better to train on more and more data sets. And as a result, you can just get less and less curation. And so now poisoning becomes something that's actually potentially possible. And so what we started by doing was looking at what could you achieve with poisoning? Like, is it possible that if someone could poison, let's say, 1% of the data set, that they would succeed? And the answer is yes. And then we started looking at, well, what about 0.1%? And in the case of semi-supervised learning, the answer is yes. Okay, well, what about less? What about 0.01%? What about 0.001%? And it turns out to poison a, okay, I'll say the word, multimodal contrastive self-supervised learning model, that the answer is something like 1 in 10,000 images need to be malicious. Okay, so what is this kind of classifier? Multimodal means like text to image. Um, Contrastive is like the type of loss that is used to train on. Self-supervised means it's like there's no like sort of strong annotations. Um, and so there's this like clip is like a very good example of this for the OpenAI model that aligns image and text pairs. And for this kind of model, yeah, we need to poison this very small rate of roughly 1 in 10,000 images, which 1 in 100,000, yeah, something like this, which is a very small number.
It's a very small number in the ratio, but compared to the number of images that are used to train it, it's still a lot of images.
Yeah, yeah, okay, very good. Yes. So how many images we use to train clip? Roughly 400 million. Right. So 1 in 10,000 is like, okay, I'm doing math in my head. Yeah, 40,000. 1 in 100,000 is 4,000. So like we're like within the realm of like what you could possibly put online. Um, actually, well, it turns out that as you scale up the models, it gets easier to poison. The 1 in 10,000, 1 in 100,000 number was for smaller data sets. We ran this on essentially clip with 400 with 400 million training images, and the number was a couple thousand images to poison. So yeah, so a couple thousand images. But you raise a good point. Like, how in the world is an adversary going to get 4,000 images that they could poison in your data set? Okay, so here's a paper that by the time that this recording goes live, the paper will be on archive. Okay, how do people train models like Clip? Well, what they do is they use data sets like Lion 400 million or Lion 5 billion. Lion is an enormous data set. It has 400 million or 5 billion images. It's very hard for an academic to publish 400 million images. Like Lion 400 million is 10 terabytes on disk. Lion 5 billion is 100 terabytes. This is too big to distribute. So instead, what people do is they distribute the data set as a collection of URLs and captions. They say, like, your problem how you download the data set. I'm just giving you these URLs and the captions to go download them from. And the data set was probably clean when the Lion people collected it. Like, it probably was good data. They checked it fairly loosely, but it probably was pretty good. Here's something fun about the world, though. Domain names sometimes expire, and when domain names expire, anyone can buy them. In particular, I can buy them. So I now own 0.01% of Lion. Anyone in the world who's downloaded Lion in the last 6 months has like implicitly trusted me to not send them malicious images.
And is that because there is a fairly high degree of concentration in the data set around one particular domain that was expired?
Yeah, we bought we spent like $100 or something. We bought 6 domains.
Wow.
Right, and
Huh.
so anyone could do this. We bought 3 of the most popular domains and 3 random ones because we were doing a research study to try and understand the impact of vulnerability. So you could have gotten a little bit more for a little bit less money, but yeah, it's a pretty good amount. Like it's in particular larger than the fraction you need to do a poisoning attack. So like with the images that we have taken, like we could, if we wanted, have been malicious in many ways. We just decided not to. And so when people tell me now poisoning isn't the thing I have to worry about, it's like, as long as you trust me to not poison your data set, then yes. But like I now have a server that is getting your requests and I am politely sending 404. But like if I sort of one day become evil, I can change this. Fortunately for this one vulnerability, it's actually fairly trivial to fix. The Lion people just need to send out the hashes of the images that you should expect to download. And they now do this. So like we sort of told them, like, could you please distribute the hashes along with the URLs? And they said, oh yes, good point. We will do this now. And so as long as you check the hashes, like you're now safe against this particular attack. But like I have every reason to believe that there will be similar kinds of attacks like this that will be possible in the future.
I guess one question I've got is, you said you got six of these domains? There were, like, how many domains did you find that were, compromised, or, changed hands, or, no longer valid?
Yeah. So there were a lot. So for Lion 400 million, the rate of these expired domains is pretty low because the data set is so new. But there still were quite a lot. But the rate only goes up as data sets get older. So we looked at some data sets like conceptual captions 3 million that was constructed in 2018, and there it's even more. We get, yeah, even more of this members of this rate of expiration. And yeah, it's hard to like really precisely pin down this, like what the numbers are going to be, because every data set is unique in how it's constructed and how sort of everything works. But it's like I expect that this is like you can't rely on, it's enough domains that you can't rely on them not expiring to like as the foundation of your security. Like you have to sort of do something like hashing these images. Um, and so I mentioned like hashing the images is sort of a perfect defense in the sense that you prevent all poisoning of this nature. Um, But there's sort of two buts. The first is like the images could have been bad to begin with. Like we're not going to sort of we're not going to fix the problem completely. We're not going to say like poisoning no longer matters. We're just going to say like this very practical attack is no longer possible. The other problem is that it can cause you to lose a bunch of actually good data. So websites don't always host the same image at the same place always. Like occasionally they'll be like re-encode the image as a more efficient JPEG, or they will decide that they didn't like the lighting and they'll sort of up the contrast, or they'll crop the image in, just to make a better version of the image. And we found that for conceptual captions 3 million, this is a data set of 3.3 million images that was collected in 2018. Of these, 2.9 million of these images are still available today. This is a pretty good number. If you require that the hashes match the exact image bytes, only 1.1 million of the images still match.
Oh, wow.
So your data set goes down by a factor of 3. Now, we don't know exactly how many of this are like garbage data that we're now throwing out because the hashes don't match, but it's not a factor of 3. It might be like, another 50% or something, but like you will lose a lot of data for old data sets by checking these hashes. But it's sort of, again, this trade-off that always comes up of security versus usability, of like, would you rather have a slightly more accurate classifier or one that I can't poison? And it sort of makes this trade-off very explicit for this case.
And have you explored the poisoning threat or scenario from a LLM perspective?
Yeah, we haven't done too much on this for large language models. We've mainly studied it on these vision models, but there have been other people who have been studying it for language models, and I think, yeah, it's a really interesting question that I think is starting to see more work as people start taking more and more data. I mean, because of the scaling laws that we've seen with OpenAI's and DeepMind scaling laws, it suggests that in order to train better models, we'll just need more and more data. Like the data is going to have to come from, like, there's only so much high quality data out there. And so in order to get more data, you're just going to have to start tolerating noisier and noisier data. And so it suggests that like people are going to have to start crawling sort of the dark corners of the internet in order to be able to find more of it. So it suggests that it should be possible. Yeah, the language model case we haven't looked as much on as the image model case.
Awesome. Well, Nicholas, thanks so much for joining us to share a bit about your work, what you're up to. It's very interesting stuff.
Yeah, thank you for having me here.